Okay, this is the second part of the stationary points lecture, and we discovered last time that in order to find stationary points on a graph, we would differentiate the function. We would find out the values for x when the derivative was equal to 0, because at a stationary point the gradient is 0. We would calculate the y-coordinates and we'd use the original function for that. We'd create a nature table for each of the x coordinates of the stationary points. We would use that table to help us look at the slope before and after the stationary point, to see what the gradient was like before we became stationary and what the gradient's like a little bit after we became stationary. From that we can get a conclusion as to the shape of the stationary point or the nature. The stationary points could be a maximum turning point like this one, a minimum turning point like this one, or they could be a point of inflection. Here we've got a rising point of inflection. So there's a stationary point in the middle there, but the graph is rising beforehand, it's stationary and it's rising again. So that's a rising point of inflection. Then we get to another stationary point here and we're falling afterwards. So we've got a maximum turning point. Okay, we're going straight to the second example, which is on page 16. We're told that y equals 4x cubed minus 2x to the power of 4. So we're going to go ahead and differentiate that function. So dy by dx is equal to multiply by the power and reduce the power by 1, 12x squared minus 8x cubed. Because we're trying to find stationary points, we're going to make that equal to 0. Remember, stationary points have a gradient of 0. And now I'm going to try and factorise and solve. I can see here I can take out a common factor of 4 and a common factor of x squared. So inside the brackets I'll have 3 minus 2x. From this I can conclude that either 4x squared equals 0, which would make x equal to 0, or 3 minus 2x equals 0, which means 2x equals 3 and x is 3 over 2. It's not uncommon to have fractional values for x. So what I now know is I know the x coordinates of the stationary points. So there are two stationary points on this curve. One of them when x is 0 and the other when x is 3 over 2. I'm going to go ahead and find the y coordinates now, then we'll do the nature table. So I'm going to use my original function, y equals 4x cubed minus 2x to the power of 4, to calculate the y coordinate. So when x is equal to 0, I'll substitute that in here and be able to calculate y. So when x is equal to 0, y is 4 times 0 cubed minus 2 times 0 to the power of 4, which is just going to give us 0. When x is 3 over 2, y is going to be 4 times 3 over 2 cubed minus 2 times 3 over 2 to the power of 4. Don't try and do anything fancy at this stage, we're substituting in. Now we're going to try to calculate. When I'm cubing a fraction, I'm just cubing the top number and I'm cubing the bottom. So I'm doing that first. So 4 times 3 cubed, which is 27, over 2 cubed, which is 8, minus 2 times 3 to the power of 4, which is 81, over 2 to the power of 4, which is 16. Now at this stage I'm going to be multiplying 4 times 27 over 8. To make things a little bit easier, I'm going to do some cancelling before I multiply. So I'm going to cancel the 4 there, so it's a 1 on the top and a 2 on the bottom. I'm also going to be able to cancel a little bit on this side. 2 becomes a 1 and 16 becomes an 8. And that will give me 27 over 2 minus 81 over 8. I'm going to need to make them both into eighths. So 4 times 27 is 108. Take away 81. Eighths, which is 27 eighths. And that means our second point is 3 over 2, 27 over 8. Okay, so I now know the 2 points that are stationary, and I just need to work out what their nature is. So I'm going to create a nature table for each. So we'll start with the 0. And remember, I need to have the x, I need to have the derivative, and I need to have the slope. I'm going to have x is 0, and I want a little bit less than that, a little bit more than that. When x is 0, our derivative is 0. And I'm just going to write the derivative here so that I remember what I'm substituting into. And that's 12x squared minus 8x cubed. Now for a little bit less than 0, I'm going to be thinking about negative 1. So I'm going to be saying 12 times negative 1 squared minus 8 times negative 1 cubed. Negative 1 squared is positive 1, so that's 12. And negative 1 cubed is negative 1 times negative 8 is plus 8. Which is going to give us 20. So I have a positive gradient just before the stationary point. Now I'm going to use a little bit more than 1, a little bit more than 0, beg your pardon, and I'm going to use 1. So I'm going to have 12 times 1 squared minus 8 times 1 cubed, which is 12 minus 8, which is 4, and that's also positive. So our slope for this is going to be positive, stationary, and positive again. So that's our rising point of inflection. So our conclusion for this point is we have a rising point of inflection at 0, 0. So that's our first stationary point. Now let's go back and look at the second. So the second point, x was equal to 3 over 2. And again, I'm going to need a table with x, dy by dx, and the slope. I'm going to have 3 over 2, a little bit less than, and a little bit more than. We know that at 3 over 2 our gradient is 0. A little bit less than 3 over 2 could be 1. And actually we already worked out in the previous example that gave us a positive gradient. I'm going to keep a note of my derivative here because I'm going to use it again. It's 12x squared minus 8x cubed. A little bit more than 3 over 2. I'm going to look at a value of 2. So it's going to give me 12 times 2 squared minus 8 times 2 cubed, which is 12 times 4, which is 48, minus 8 times 8, which is 64, which will give us negative 16. So I've got a negative gradient there. So that means the shape of this slope, it's rising because it's a positive gradient, stationary, and then decreasing because it's a negative gradient. So from that I can conclude I have a maximum turning point at 3 over 2, 27 over 8. Okay, and the final example. In this example, y equals 2x plus 1 over x. We're only asked for the x coordinates, so we don't need to work out the y coordinates. Before I differentiate, I'm going to need to deal with that x, which is on the bottom of the fraction. So I'm going to say that's the same as 2x plus x to the negative 1. Now, in the original definition there, you can see it's explained the function and it's given us a condition that x cannot be equal to 0. And that's because we can't divide by 0. We've got our function in a form that we can differentiate. So I'm just going to go right ahead and differentiate. dy by dx is equal to 2 minus x to the minus 2. I'm going to tidy that up. So it's the same as 2 minus 1 over x squared. It's stationary points we're looking for, which means our gradient is going to be 0. So I can make this equal to 0. When I'm solving this, I'm not going to be factorising like I have before. I'm going to treat it like an equation and shuffle everything around till I get x on its own. So I'm going to add 1 over x squared to both sides, which means 2 equals 1 over x squared. Multiply both sides by x squared. 2x squared equals 1. Divide each side by 2 tells me that x squared is a half. And then I'm going to square root both sides. So x is the square root of a half. Now I need to remember that there are two answers. It could be plus or minus. And using my surge knowledge, that's 1 over root 2, plus or minus. So I've found the two possibilities for the x coordinates. So there are two stationary points here. One is that when x is positive 1 over root 2, and one is when x is negative 1 over root 2. I'm going to do the nature tables now for each of those points. So same as before, we are drawing a table. We're going to have x, we're going to have the derivative, and we're going to have the shape or the slope. I'm going to first pick 1 over root 2, and I want a little bit before it and a little bit after it. I know that at that exact point I've got a gradient of 0. A little bit less than, I'm going to say a half. And a little bit more than, I'm going to say 1. And I'm going to have my derivative here just to remind me what I'm substituting into. And dy by dx was equal to 2 minus 1 over x squared. So I'm going to look at the half first. So 2 minus 1 over a half squared. Now a half squared is 1 squared over 2 squared, so it's a quarter. So it's 2 minus 1 over a quarter. Dividing by a quarter is the same as multiplying by 4. So that's 2 minus 4, which is minus 2. So when x is a half, I've got a negative gradient. When x is 1, my derivative is 2 minus 1 over 1 squared, which is 2 minus 1, which is 1. So I have a positive gradient. And that means my slope is decreasing, stationary, increasing. And you can see from the shape that I've got a minimum turning point when x is equal to 1 over the square root of 2. Now I need a nature table for the second point. So, same as before, I've got x, I've got dy by dx, and I've got the slope. The stationary point I'm looking at is negative 1 over root 2. I know that at that exact point I have a gradient of 0. A little bit less than that, I'm going to use minus 1. 1 over root 2, by the way, is approximately 0.7. So negative 0.7, a little bit lower than that's going to be negative 1. A little bit bigger than that is going to be negative a half. I can't go as high as 0 because I can't substitute 0 in to this because I'd be dividing by 0. So I'm going to have to stick with the fractions. So when I've put the negative 1 in, I've got 2 minus 1 over negative 1 squared, which is just 2 minus 1, which is 1. So I have a positive gradient. When I put the negative a half in, I've got 2 minus 1 over negative a half squared. Negative half squared is a quarter. So 2 minus 1 over a quarter. And remember, dividing by a quarter is the same as multiplying by 4. So that's 2 minus 4, which gives me negative 2. So I have a negative gradient there. So this stationary point is increasing, then it's stationary, and then it's decreasing. So I have a maximum turning point when x equals negative 1 over root 2. Okay, so these examples are all complete now. Just to double check, this is the second lesson on this, so we've already summarised. But if the gradient is increasing before the stationary point, it then becomes stationary, and then it's decreasing after the stationary point, what's the nature of that stationary point? And number 2, when you're using the nature table and you're calculating these values to work out the gradient before and after your stationary point, what do you substitute into? Okay, and we're now ready for exercise 6M. Questions 1 to 6 are unit level, and questions 7 to 9 are level C.